Alright, so now that we've seen that different molecules can actually serve as both acids and bases, particularly with water in our last example, we should describe the term that describes those molecules that can be an acid in some cases and a base in other cases. And so that term is either amphiprotic, or we could call it amphoteric. So depending on which textbook, which website you're looking at, you might see either one of these terms. The root of these is amphi, right? Or amph, and so that's like amphibian, right? So amphibians live on both water and on land, and so amphiprotic means you can be both accepting a proton or donating a proton. So it's amphi and prot for the proton. So an example here other than water is going to be hydrogen carbonate, and then we see in this example it starts off with a proton, and then when it's over on the right side of our reaction, it is going to be missing that proton. So now it is just carbonate. So in this instance, we have something giving up a proton. This hydrogen carbonate is going to be an acid. It has formed just carbonate on the right side, so that is the conjugate base. That would be one of our pairs. And then we also have water. Water is over here on the left side. It is going to accept a proton, so it is going to start off as a base. And then when it's over here, it's the conjugate acid. And so that by itself does not make this hydrogen carbonate amphiprotic. We have to look at a second reaction equation to see an instance of where we might see this amphiprotic characteristic. So now we have that same hydrogen carbonate on the left side. On the right side of this reaction equation, it has not given up a proton, it's actually accepted a proton from water. So if it's going to accept a proton, that is going to make it a base. After it accepts that proton, it's going to become the conjugate acid. And so that is our pair. And then our other pair is this water. It's going to have to be the acid because it's donating a proton. And after it donates a proton, it becomes a conjugate base. So that's our other pair. And so the reason that we call this molecule hydrogen carbonate amphiprotic or amphoteric is because in one of these instances it's acting as an acid, and in the other instance it's acting as a base. So we have to have these molecules that contain a hydrogen in order for them to be acidic in some cases, but they also have to have the capacity to accept another proton, and so this minus sign here is helping us understand that it can accept a proton and then go to having a nice neutral charge. So let's look at some additional examples. So if we give you a list, which of these following species are amphiprotic, amphoteric, and then can we write chemical equations illustrating this character in these species? So the things that we want to look for are things that we already know, right? Like water. Sometimes water can act as an acid, sometimes as a base, so we're going to say yes, this one should be good. This next molecule in B has protons and has that negative charge, so it ought to be able to accept another proton and give up a proton. So let's say yes for that one. This S2-, well, it looks like it could probably accept an H, but it has no H to give, so we're going to say no to that one. This carbonate by itself does not have a proton to give up, so it could accept but not give, so let's say no there. And then this final one, we do again have a molecule that has an H and a minus sign, so it is probably going to be able to accept one more proton and donate a proton, so we'll say yes to that. So what are the next part of this problem is asking is, can we write those chemical equations that describe what's happening? In the first example, we've already seen that water can be kind of amphiprotic just with itself, but here's an example with another compound that helps demonstrate that. In this example, we have the Bronsted-Lowry base, this nitrogen-containing base, and so it is going to be able to pull a proton off of water, so that means water's donating a proton, so we have water acting as an acid, donating that proton, and then becoming that conjugate base. In another scenario, we could have water acting as a base if it accepts a proton. So if you put water next to a very good acid, like HCl, then it is going to start acting more basic because you've got a really good acid in there. So this case, we're going to have water acting as a base, accepting a proton, becoming that conjugate acid in the end. So that's one example for water. We had two other things that we highlighted as being amphiprotic, and so H2PO4 acting as an acid needs to give up a proton. We had two protons over here on the right side. We've now given up one of those protons. That proton went from the H2PO4 to water, and that H2 becomes an H3. H2PO4 acting as a base, well, in order to do that, it needs to be able to accept a hydrogen, a proton, so our H2 becomes H3. It got that proton from our water, and so that H2O becomes an HO, right, a hydroxide. And another example, our HSO4 as an acid, we have it here on the left. It still has a proton. It's going to give up that proton to water. It's just going to leave a sulfate ion after it gives up that proton. And then acting as a base, that means it has to accept a proton. So our H on the left is going to become an H2 on the right. It grabbed a proton from water, and so now H2O becomes HO, or just OH. So those are some examples that help work out this idea that you can have compounds that can serve as both acids or bases, really just depending upon the scenario that you put them in. What are you mixing them with? Are you mixing them with something that is a better acid or a better base, say a strong acid or a strong base, and that can kind of flip the role of your compound if it's not a strong acid or a strong base. So that concludes this section just on this small topic and term, and so you can go ahead and close this one and move on to the next topic.